Hey guys, I want to start tonight with a thought that I find both strange and wonderful. Right now, as you're listening to this, you're moving through space at incredible speed. Earth spins at over 1,000 kilometers per hour. We orbit the sun at 100,000 kilometers per hour. Our entire solar system races around the Milky Way at over 800,000 kilometers per hour. And the Milky Way itself, along with everything in it, is moving through space. All of this motion, every bit of it, traces back to a single moment nearly 14 billion years ago. Have you ever thought about the fact that everything, including you, is still moving outward from that initial expansion? What do you think that moment was actually like? Drop a comment and tell me. I'm genuinely curious how people imagine it. Tonight, we're exploring the beginning of everything, examining what we know about how the universe came to be, and how scientists piece together this story from observations we can make today. This isn't about speculation or philosophy. It's about following the evidence, tracing cosmic history backward through time, and understanding what the data actually tells us about the earliest moments. We'll examine the observations that support our current understanding, from the expansion of space itself to the faint radiation filling the universe, from the abundance of light elements to the formation of the first structures. Along the way, we'll explore what happened during those initial moments, how matter and energy emerged, and how the universe evolved from a hot, dense state into the vast cosmos we observe today. Let's begin with what we can observe directly and work our way backward toward the beginning. When astronomer Edwin Hubble observed distant galaxies in the late 1920s, he noticed something remarkable. The light from these galaxies appeared shifted toward redder wavelengths. More distant galaxies showed greater redshift. This pattern, now called Hubble's law, revealed something fundamental about the universe. The redshift occurs because space itself expands. As light travels through expanding space, its wavelength stretches along with the expansion. The farther light travels, the more expansion occurs during its journey, producing greater redshift. This relationship between distance and redshift provided the first evidence that the universe is not static, but expanding. If the universe is expanding now, then it must have been smaller in the past. Trace this expansion backward through time, and you reach a point where everything in the observable universe occupied an incredibly small region. This realization that the universe emerged from an extremely dense and hot state forms the foundation of what we call cosmology. The expansion itself represents not objects moving through space, but space itself growing larger. Galaxies don't move away from each other in the traditional sense. They remain largely stationary within space, while the space between them increases. This distinction matters because it explains how distant galaxies can recede faster than light without violating relativity, which limits motion through space, but not the expansion of space itself. Observations of this expansion allow astronomers to calculate when it began, by measuring how fast galaxies recede and how far away they lie. Cosmologists determine the age of the universe. Multiple independent methods, including observations of the cosmic microwave background and measurements of the oldest stars, converge on an age of approximately 13.8 billion years. This expansion began not from a specific location in existing space, but from everywhere simultaneously. In the earliest moments, all of space, everything that would become the observable universe, existed in an extremely hot, extremely dense state. Then, approximately 13.8 billion years ago, expansion began. What exactly initiated this expansion remains one of physics' deepest questions. Our current understanding breaks down at the very beginning. At the moment, cosmologists call the initial singularity. The laws of physics, as we understand them, cannot describe conditions at infinite density and temperature. Developing a theory of quantum gravity, combining quantum mechanics with general relativity, might eventually explain what happened at this earliest instant. However, we can trace cosmic history to extraordinarily early times using known physics. Within a tiny fraction of a second after expansion began, the universe underwent a brief period of exponentially rapid expansion called cosmic inflation. During inflation, space expanded faster than light, growing by many orders of magnitude in less than a trillionth of a second. Inflation explains several observed properties of the universe. It explains why space appears flat rather than curved, why the cosmic microwave background looks remarkably uniform in all directions, and why the observable universe contains regions that should never have been in causal contact, yet share similar properties. During inflation, quantum fluctuations, tiny variations in energy density, got stretched to cosmic scales. These fluctuations eventually became the seeds from which all structure, galaxies, stars, planets, formed. The pattern of these fluctuations, preserved in the cosmic microwave background, matches theoretical predictions with remarkable precision. After inflation ended, the universe contained enormous energy, but little in the way of particles or radiation. This energy rapidly converted into particle-antiparticle pairs through a process called reheating. The universe became filled with an incredibly hot, dense plasma of fundamental particles. During the first microsecond, quarks and gluons, the building blocks of protons and neutrons, existed freely in this plasma. As the universe expanded and cooled, quarks combined into protons and neutrons through a transition called quark confinement. This occurred when the universe was perhaps 1 microsecond old. By the time the universe reached 1 second of age, it had cooled to approximately 10 billion degrees Celsius. At these temperatures, protons and neutrons could exist, but heavier atomic nuclei remained unstable. The universe consisted primarily of photons, neutrinos, electrons, positrons, and smaller numbers of protons and neutrons, between approximately 1 and 3 minutes after the beginning. Temperatures dropped enough for nuclear fusion to occur. Protons and neutrons combined to form the nuclei of light elements, primarily helium along with trace amounts of deuterium, helium-3, and a lithium. This process, called primordial nucleosynthesis, produced the first atomic nuclei in the universe. The exact abundances of these light elements depend on conditions during nucleosynthesis, particularly the density of protons and neutrons. Calculations predict approximately 25% of ordinary matter should be helium by mass, with smaller amounts of the other light elements. Observations of the oldest gas clouds, which have undergone minimal processing by stars, show element abundances matching these predictions with remarkable accuracy. This agreement between predicted and observed abundances provides strong evidence for the hot, dense early universe described by the theory. No alternative explanation has successfully predicted these specific abundances. The match between theory and observation, across multiple elements, represents one of the major successes of modern cosmology. After nucleosynthesis concluded, around 20 minutes after the beginning, the universe continued expanding and cooling. However, it remained too hot for neutral atoms to form. Electrons remained free rather than being bound to atomic nuclei. This plasma of charged particles scattered photons constantly, making the universe opaque to radiation. This opaque phase lasted approximately 380,000 years. During this time, expansion continued. Structure began forming as denser regions pulled in surrounding matter through gravity. but the universe remained filled with ionized plasma that scattered light. Eventually, when the universe cooled to approximately 3,000 degrees Celsius, electrons combined with atomic nuclei to form neutral hydrogen and helium atoms. This transition, called recombination, fundamentally changed how light interacted with matter. Neutral atoms scatter photons much less efficiently than free electrons. When recombination occurred, the universe suddenly became transparent. Photons could travel freely through space rather than being constantly scattered. The radiation present at that moment, the light last scattered before the universe became transparent, has been traveling through space ever since. This radiation, stretched by 13.8 billion years of cosmic expansion, now appears as microwave radiation filling all of space. We call it the cosmic microwave background. Its discovery in 1964 by Arno Penzias and Robert Wilson, working at Bell Telephone Laboratories, provided crucial evidence for the expanding universe model. The cosmic microwave background shows several remarkable properties. Its spectrum matches a blackbody, an ideal thermal radiator, at a temperature of 2.7 Kelvin, just above absolute zero. This perfect blackbody spectrum, measured with extraordinary precision by satellites including COBE and Planck, matches theoretical predictions exactly. The temperature appears remarkably uniform across the sky. Variations amount to only 1 part in 100,000. This uniformity, combined with the blackbody spectrum, indicates the universe passed through a phase where all regions reached thermal equilibrium, exactly as predicted by cosmology. However, tiny variations do exist in the cosmic microwave background temperature. These variations, carefully mapped by satellites, reflect density fluctuations present when the universe was 380,000 years old. Denser regions appear slightly warmer, less dense regions slightly cooler. These density variations, originating from quantum fluctuations during inflation, represent the seeds from which all cosmic structure grew. Gravity amplified the initial variations over billions of years. Denser regions attracted surrounding matter, growing denser still, eventually forming galaxies and galaxy clusters. The pattern of variations in the cosmic microwave background, analyzed statistically, matches predictions from inflation theory with remarkable precision. The cosmic microwave background represents the farthest back we can see using electromagnetic radiation. Before recombination, the universe was opaque. We cannot observe earlier epochs with light, but other signals might penetrate this barrier. Neutrinos, for instance, decoupled from matter much earlier, perhaps 1 second after the beginning. Detecting this cosmic neutrino background would provide information about even earlier times. Gravitational waves, ripples in space-time itself, decouple even earlier, potentially carrying information from the inflationary epoch itself. Detecting primordial gravitational waves represents one of observational cosmology's major goals. Their detection would provide direct evidence of inflation and reveal conditions during the universe's first tiny fraction of a second. After recombination, the universe entered what cosmologists call the Dark Ages. With no stars, yet formed, the universe contained only neutral hydrogen and helium gas, slowly collapsing under gravity into denser regions. This period lasted several 100 million years. Eventually, gravity pulled gas into regions dense enough to ignite nuclear fusion. The first stars formed, perhaps 400 million years after the beginning. These early stars, forming from pure hydrogen and helium with no heavier elements, likely differed from modern stars. Many probably achieved enormous masses, burning intensely and expiring quickly in supernovae that enriched surrounding gas with heavier elements. The ultraviolet radiation from these first stars began ionizing surrounding hydrogen, starting a process called reionization. Over hundreds of millions of years, radiation from stars and early galaxies ionized most of the neutral hydrogen in the universe. The universe transitioned from neutral and dark to ionized and transparent to ultraviolet light. Galaxies began forming through the gravitational collapse of dark matter and ordinary matter. Dark matter, invisible material interacting primarily through gravity, began clumping together earlier than ordinary matter because it doesn't interact with radiation. These dark matter concentrations created gravitational wells into which ordinary matter fell, accelerating galaxy formation. The first galaxies appeared perhaps 500 million years after the beginning. Early galaxies looked different from modern ones. Smaller, more irregular, actively forming stars at high rates. Over billions of years, galaxies merged, grew larger, developed organized structures, and evolved into the variety of forms we observe today. Our Milky Way galaxy formed through the merger of many smaller galaxies over billions of years. The oldest stars in our galaxy, found in globular clusters, and the galactic halo, formed over 12 billion years ago, when the universe was less than 2 billion years old. These ancient stars contain very few heavy elements, reflecting that they formed from gas, enriched by only a few previous stellar generations. Younger stars, including our Sun, formed later from gas progressively enriched by many generations of stars that lived, fused lighter elements into heavier ones, and returned that material to the interstellar medium through stellar winds and supernovae. The Sun, containing approximately 2% heavy elements by mass, formed about 4.6 billion years ago from a molecular cloud already enriched by billions of years of stellar processing. The universe today, 13.8 billion years after the beginning, continues expanding. Observations show this expansion is accelerating, driven by dark energy, a mysterious component constituting approximately 68% of the universe's total energy content. Dark matter contributes about 27%, while ordinary matter, everything we can see, accounts for only about 5%. Understanding dark energy represents one of modern physics' greatest challenges. We observe its effects through cosmic acceleration, but we don't know what it is. The simplest explanation treats dark energy as a property of space itself, a constant energy density that doesn't dilute as space expands. This cosmological constant, if correct, implies expansion will continue accelerating indefinitely. The story of the universe, as we currently understand it, traces from an incredibly hot, dense beginning through inflation, particle formation, nucleosynthesis, recombination, the formation of first stars and galaxies, and continuing evolution into the structured cosmos we observe today. Each phase left evidence we can observe, from the abundances of light elements to the cosmic microwave background to the distribution of galaxies across space. This understanding comes from combining observations across many wavelengths with theoretical models based on established physics. The predictions match observations with remarkable precision across independent tests. The abundances of light elements, the properties of the cosmic microwave background, the large-scale distribution of galaxies, the expansion history of the universe. All these independent lines of evidence converge on the same cosmic history. Of course, many questions remain. What initiated the beginning? What is dark matter? What is dark energy? How did the first stars form? When did the first galaxies appear? How did supermassive black holes grow so quickly in the early universe? Each answered question reveals new mysteries waiting beneath. The cosmic microwave background provides a snapshot of the universe at 380,000 years old. Observing earlier times requires detecting signals that penetrated the opaque plasma. such as neutrinos or gravitational waves. Observing later times. The formation of the first stars and galaxies requires powerful telescopes capable of detecting extremely distant, and therefore ancient, objects. Modern telescopes, including the James Webb Space Telescope launched in 2021, can observe galaxies forming within the first billion years after the beginning. These observations reveal how quickly structure emerged, how early galaxies differed from modern ones, and how the universe evolved during its early history. The expansion of the universe creates an interesting relationship between distance and time. When we observe distant objects, we see them not as they exist now, but as they existed when their light began traveling toward us. Looking deeper into space means looking further back in time. The most distant galaxies observable lie over 13 billion light-years away, meaning we observe them as they appeared when the universe was less than 1 billion years old. This relationship allows astronomers to trace cosmic history by observing objects at different distances. Nearby galaxies reveal recent cosmic history. More distant galaxies show earlier epochs. The cosmic microwave background shows the universe at 380,000 years old. Together, these observations map the evolution of the universe across 13.8 billion years of history. Understanding the beginning requires combining observations with theoretical physics. General relativity describes how space-time behaves, how it expands and curves in response to matter and energy. Quantum mechanics describes particle physics, nuclear reactions, and the behavior of matter at extremely high densities and temperatures. Together, these frameworks allow cosmologists to model cosmic history from the inflationary epoch onward. The agreement between predictions and observations, across multiple independent tests, provides strong support for our current understanding. The theory successfully predicts the abundances of light elements, the properties of the cosmic microwave background, the large-scale distribution of galaxies, and the expansion history of the universe. No alternative explanation has matched this predictive success, yet our understanding remains incomplete. We cannot yet describe the very beginning itself, the moment when expansion started. Perhaps future theories, combining quantum mechanics and general relativity into a theory of quantum gravity, will provide that description. Perhaps new observations will reveal unexpected phenomena requiring revised models. Science proceeds by testing predictions against observations. When predictions match, confidence in the theory grows. When observations conflict with predictions, theories must be modified or replaced. The history of cosmology includes many such revisions. From the realization that the universe expands to the discoveries of dark matter and dark energy. Current cosmological models, sometimes called the Standard Model of Cosmology, or Lambda CDM, incorporate cold dark matter and a cosmological constant representing dark energy. These models match observations remarkably well across all tested predictions, yet they require components, dark matter and dark energy, whose fundamental nature remains unknown. Understanding these components represents a major goal of contemporary physics. Multiple experiments search for dark matter particles. Observational programs measure cosmic expansion history to constrain dark energy properties. Theoretical physicists develop models attempting to explain these phenomena from first principles, the beginning of the universe. While it occurred nearly 14 billion years ago, remains accessible to scientific investigation through the evidence it left behind. The expansion we observe today, the light elements present in the oldest gas clouds, the cosmic microwave background, radiation filling all of space, the distribution of galaxies across the cosmos, all these provide information about conditions in the early universe. From this evidence, scientists reconstruct cosmic history. The story that emerges of expansion from an incredibly hot and dense state matches predictions across independent tests with extraordinary precision. The universe as we observe it today, with its billions of galaxies spread across vast distances, all emerged from that beginning nearly 14 billion years ago. The atoms in your body, the oxygen you breathe, the carbon in your cells, the iron in your blood, originated in that early universe or in stars that formed later. The hydrogen in water molecules formed during primordial nucleosynthesis in the first few minutes. Heavier elements formed through fusion in stars or during supernovae. You consist literally of material created in the early universe and processed through stellar cycles. This connection between cosmic history and everyday existence demonstrates how understanding the beginning informs understanding of present conditions. The universe's evolution over 13.8 billion years, from a hot plasma to the structured cosmos we inhabit, created the conditions allowing planets, chemistry, and ultimately, life to exist. Looking forward, the universe will continue evolving. Stars will continue forming, though at declining rates as gas reservoirs diminish. Galaxies will continue merging under gravity's influence. In approximately 4 billion years, the Milky Way and Andromeda galaxies will begin their merger, eventually combining into a single larger galaxy. On much longer timescales, star formation will gradually cease as available gas is consumed or dispersed. Galaxies will fade as their stellar populations age. If dark energy continues driving accelerating expansion, distant galaxies will recede beyond observational reach, their light stretched beyond detectability. These future developments, unfolding over billions or trillions of years, represent natural consequences of physical processes operating today. The universe doesn't undergo catastrophic transitions but evolves gradually under the influence of gravity, nuclear fusion, and cosmic expansion. The story of the universe, from beginning to present and into the future, follows from applying known physical laws across cosmic scales and timescales. While many details remain uncertain, the broad outline, supported by multiple independent lines of evidence, provides our best current understanding of cosmic history. Understanding the beginning represents one of science's remarkable achievements. From observations we can make today, we reconstruct events that occurred nearly 14 billion years ago. We trace the evolution of matter and energy from an incredibly hot, dense state through the formation of atoms, stars, galaxies, and the emergence of structure across vast distances. This understanding continues developing as new observations refine measurements and potentially reveal unexpected phenomena. Each advance, whether theoretical insight or observational discovery, extends our knowledge of cosmic history and structure. The universe we observe, vast and ancient, emerged from a beginning we can study through its lasting effects. The evidence surrounding us, from the expansion of space to the radiation filling it, from the abundances of elements to the distribution of galaxies, all trace back to that initial moment when expansion began. Tonight's journey through cosmic history, from the beginning forward to the present, reveals a universe operating according to consistent physical principles across enormous spans of space and time. The same forces that shaped the early universe continue operating today, driving expansion, powering stars, organizing matter into structures spanning from planets to galactic superclusters. We observe this universe from one particular moment in its history, 13.8 billion years after the beginning, during an epoch when stars actively form, when galaxies retain abundant gas, when structure continues evolving through gravitational interaction. This represents a dynamic period in cosmic evolution. Neither the chaotic early universe nor the dim future after star formation ceases. From this vantage point, Using instruments that detect electromagnetic radiation across many wavelengths, we piece together the story of everything. We trace light traveling billions of years. We decode information encoded in that light about temperatures, compositions, motions, distances. We reconstruct histories of objects we'll never visit, events we'll never witness directly, processes operating on scales far exceeding direct human experience. This ability to transcend immediate perception through observation and reasoning represents science's power. We need not have witnessed the beginning to understand it. We need not travel to distant galaxies to study them. By carefully analyzing signals reaching Earth from across the cosmos, we map structure and trace history spanning the observable universe. The beginning, that moment when expansion started nearly 14 billion years ago, determined much about the universe we observe today. The initial conditions, the energy density, the balance between matter and radiation, the quantum fluctuations that seeded structure. All these set the stage for everything that followed. From those initial moments emerged atoms, stars, galaxies, planets, and eventually, on at least one world, life capable of contemplating its own cosmic origins. The universe gave rise to observers who can study the universe itself, a remarkable development in cosmic evolution. Understanding the beginning helps us understand our place within cosmic history. We exist neither at the beginning nor at the end, but somewhere in the middle chapters of an ongoing story. The universe formed long before Earth existed. It will continue long after Earth no longer exists. Yet during this brief overlap, during this narrow window when conditions allow complex structures like planets and life, we can observe, measure, and understand the cosmos that gave rise to us. The evidence for the beginning, from expansion to element abundances to background radiation, comes from observations we can make today. This evidence, interpreted through established physical theories, reveals a consistent story of cosmic evolution over 13.8 billion years. The agreement between independent lines of evidence, the precision of predictions matched by observations, provides confidence in this reconstruction of cosmic history. Many questions remain unanswered. The fundamental nature of dark matter and dark energy, the exact mechanism of inflation, the detailed process of galaxy formation, the origin of supermassive black holes. Each answered question reveals deeper questions waiting beneath. Science continues investigating these mysteries through new observations and theoretical developments. Future telescopes will probe earlier cosmic epochs. New experiments will search for dark matter particles. Advancing theory might explain currently mysterious phenomena. The process continues, driven by curiosity about cosmic origins and evolution. As we conclude this exploration of the beginning, we return to the present, to this moment 13.8 billion years after expansion started. The universe continues evolving, expanding, organizing matter into structures under gravity's influence. Stars form from collapsing gas clouds. Galaxies merge under gravitational attraction. The cosmic web of structure grows more pronounced as expansion carries unbound regions apart, while gravity pulls bound structures together. We observe all this from Earth, one planet among countless others, orbiting a star among hundreds of billions, in a galaxy among trillions visible across the observable universe. From this vantage point, we trace our cosmic origins, recognizing that everything we observe, everything we are, emerged from that beginning nearly 14 billion years ago. The universe, as we understand it today, vast and ancient, filled with structure at every scale, all traces back to that initial moment when expansion began. The evidence surrounds us. The story it tells of evolution from hot plasma to structured cosmos represents one of humanity's great intellectual achievements, understanding our origins through careful observation and thought. Let's explore more deeply how scientists piece together this story, examining the specific observations and measurements that support our understanding of cosmic history. The cosmic microwave background, discovered accidentally in 1964, provides the most direct observational evidence for the hot early universe. Arno Penzias and Robert Wilson, working at Bell Telephone Laboratories in New Jersey, were testing a sensitive radio antenna when they detected a persistent background noise they couldn't eliminate. This noise appeared equally strong in all directions, independent of time of day or season. After eliminating all possible sources of interference, including effects from New York City, atmospheric conditions, and even pigeon droppings on the antenna, they realized they had detected something cosmic. Nearby at Princeton University, physicist Robert Dicker and his colleagues had been preparing to search for exactly this radiation, predicted by theory, but not yet observed. The radiation Penzias and Wilson detected represented the cooled remnant of thermal radiation from the hot early universe. When recombination occurred, photons stopped scattering off free electrons and began traveling freely through space. Those photons, stretched by 13.8 billion years of cosmic expansion, now appear as microwave radiation at a temperature of 2.7 Kelvin. Early measurements showed this radiation came equally from all directions, suggesting a uniform early universe. More precise measurements revealed tiny variations, temperature differences of only 1 part in 100,000 across the sky. These variations, first detected by the COBE satellite in 1992, provided crucial information about the early universe. The pattern of these temperature variations matches predictions from inflation theory with remarkable precision. Inflation predicts quantum fluctuations during the exponential expansion phase would create density variations following a specific statistical pattern. These variations would appear in the cosmic microwave background as temperature differences, with denser regions appearing slightly warmer. The COBE satellite measured the large-scale pattern of these variations. The WMAP satellite, launched in 2001, measured the pattern in greater detail across a range of angular scales. The Planck satellite, launched in 2009, provided even more precise measurements, constraining cosmological parameters to unprecedented accuracy. Analysis of these measurements reveals information about cosmic composition, geometry, age, and expansion history. The data indicates space is flat, or very nearly so, to within measurement precision. The universe's age comes out to 13.8 billion years with an uncertainty of less than 1%. The composition, about 68% dark energy, 27% dark matter, and 5% ordinary matter, emerges from analyzing how radiation and matter interacted during recombination. The cosmic microwave background also reveals information about conditions during inflation. Inflation predicts gravitational waves produced during exponential expansion would create a specific pattern in the polarization of background radiation. Detecting this pattern, called B-mode polarization, would provide direct evidence of inflation and reveal the energy scale at which it occurred. Several experiments currently search for this primordial B-mode signal. The detection would represent a major discovery, confirming inflation and providing information about physics at energy scales far beyond what particle accelerators can reach. So far, the signal has not been definitively detected, placing constraints on inflationary models, but leaving the question open. Beyond the cosmic microwave background, the abundances of light elements provide independent evidence for the hot early universe. During the first few minutes after expansion began, when temperatures ranged from billions to hundreds of millions of degrees, Nuclear fusion reactions combined protons and neutrons into light element nuclei. The specific abundances produced depend critically on conditions during this nucleosynthesis epoch: temperature, density, and the ratio of protons to neutrons all affect which reactions occur and how much of each element forms. Calculations show that approximately 25% of ordinary matter should emerge as helium-4, with smaller amounts of deuterium, helium-3, and lithium-7. Observations of the oldest gas clouds, which formed early in cosmic history before being significantly processed by stars, show element abundances matching these predictions. The helium abundance measures close to 25% by mass. Deuterium appears at predicted levels. Lithium, though showing some discrepancy, generally matches expectations within observational uncertainties. This agreement between predicted and observed abundances across multiple elements provides strong evidence that the universe passed through a hot, dense phase when nuclear reactions occurred. No alternative explanation has successfully predicted these specific abundance ratios. The precise match, especially for helium and deuterium, represents a major success of cosmology. The formation of structure in the universe, from galaxies to galaxy clusters to the cosmic web, also supports our understanding of cosmic history. Computer simulations, starting from initial conditions, matching the cosmic microwave background and evolving matter forward in time under gravity, produce structures remarkably similar to what we observe. These simulations require including dark matter, which interacts primarily through gravity and began clumping earlier than ordinary matter. Dark matter created gravitational wells into which ordinary matter later fell, accelerating structure formation. Without dark matter, simulations fail to reproduce observed large-scale structure. Multiple independent observations indicate dark matter exists. Galaxy rotation curves, measuring how fast stars orbit at various distances from galactic centers, show velocities too high to be explained by visible matter alone. Gravitational lensing, the bending of light by mass, reveals more mass in galaxy clusters than we can see. The cosmic microwave background shows patterns consistent with specific amounts of dark matter affecting how radiation and matter interacted during recombination. While we observe dark matter's gravitational effects, its fundamental nature remains unknown. It doesn't emit or absorb light. It doesn't interact significantly with ordinary matter except through gravity. Multiple experiments search for dark matter particles, attempting direct detection or looking for signals from dark matter annihilation or decay. So far, the particle nature of dark matter remains unidentified. Dark energy presents an even deeper mystery. Discovered through observations of distant supernovae in the late 1990s, dark energy appears to constitute the majority of the universe's energy content. It causes cosmic expansion to accelerate, pushing galaxies apart at ever-increasing rates. The simplest explanation treats dark energy as a cosmological constant, an inherent property of space itself with constant energy density. As space expands, more space is created, and because energy density remains constant, total dark energy increases. This creates a repulsive effect that strengthens as the universe grows, driving accelerating expansion. Observations of distant supernovae, combined with measurements of the cosmic microwave background and large-scale structure, constrain dark energy properties. The data favor a cosmological constant, but allow for more complex possibilities where dark energy properties might evolve with time. Understanding dark energy represents one of physics' most important unsolved problems. The expansion history of the universe, traced through observations of distant objects, reveals how expansion evolved over cosmic time. In the early universe, dominated by matter and radiation, expansion gradually slowed under gravity's influence. This deceleration continued for approximately 9 billion years. Then, as the universe grew larger and matter density decreased through expansion, dark energy began dominating cosmic dynamics. Expansion started accelerating approximately 5 billion years ago. This acceleration continues today and appears to be strengthening as dark energy becomes increasingly dominant relative to matter. The transition from deceleration to acceleration left signatures we can observe, distant supernovae, showing how bright objects appeared billions of years ago, reveal expansion rates at different cosmic epochs. The cosmic microwave background, showing conditions 13.8 billion years ago, constrains early expansion. Large-scale structure, shaped by expansion over billions of years, reveals how expansion affected structure formation. Together, these observations map cosmic expansion history from the early universe to the present. The data match predictions from models including dark energy, providing confidence in our understanding despite not knowing dark energy's fundamental nature. The formation of the first stars and galaxies, occurring hundreds of millions of years after recombination, marks another major transition in cosmic history. Before first stars formed, the universe contained only neutral hydrogen and helium gas, dark matter, and radiation. No sources of light existed except the fading glow of the cosmic microwave background, stretched by expansion into infrared wavelengths. Gravity pulled matter into denser regions, concentrating gas and dark matter into clumps. When gas concentrations reached sufficient density, gravitational heating raised temperatures high enough to ignite fusion. The first stars formed, perhaps 400 million years after the beginning, though exact timing remains uncertain. These first stars, called population 3 stars, formed from pure hydrogen and helium with no heavier elements, lacking heavy elements, which help cool gas clouds. These early stars likely achieved much larger masses than typical modern stars. Many probably exceeded 100 solar masses, burning intensely and expiring quickly in powerful supernovae. When these massive stars exploded, they scattered newly synthesized heavy elements into surrounding gas. Later, stellar generations formed from this enriched material, gradually increasing the heavy element content of the interstellar medium. Each generation of stars added more heavy elements, building up the chemical complexity we observe today. Our Sun, forming approximately 4.6 billion years ago, contains roughly 2% heavy elements by mass. This abundance reflects billions of years of stellar processing, with countless previous stars creating and dispersing the heavy elements incorporated into the solar nebula, from which our solar system formed. Observing the first stars directly remains challenging because of their extreme distance. Light from objects that far away has been traveling nearly the entire age of the universe, arriving heavily redshifted and extremely faint. Current telescopes can detect galaxies forming within the first billion years, revealing rapid structure formation. But individual population 3 stars remain beyond direct observation. The James Webb Space Telescope, launched in 2021, was designed specifically to observe the earliest galaxies and potentially detect signatures of the first stars. Operating primarily in infrared wavelengths, it can detect light from very distant objects whose emission has been redshifted from visible to infrared. Early observations revealed galaxies that formed surprisingly quickly, earlier and more massive than some models predicted, requiring refinements to our understanding of early galaxy formation. The reionization of the universe, caused by radiation from the first stars and galaxies, represents another major transition. Before reionization, hydrogen throughout the universe existed primarily as neutral atoms. Ultraviolet radiation from stars began ionizing this hydrogen, creating bubbles of ionized gas around each galaxy. As more stars formed and more galaxies appeared, these ionized bubbles grew and eventually overlapped. Over hundreds of millions of years, most hydrogen in the universe became ionized. This transition, called the epoch of reionization, occurred roughly between 400 million and 1 billion years after the beginning. Evidence for reionization comes from several sources. The cosmic microwave background shows subtle polarization patterns created when photons scattered off free electrons during reionization. Observations of distant quasars, active galactic nuclei emitting intense radiation, reveal absorption by neutral hydrogen along the line of sight, providing information about when reionization completed. Understanding reionization requires understanding when and how the first stars and galaxies formed. Current observations constrain but don't fully determine reionization history. Future observations, particularly from radio telescopes detecting the 21-centimeter line of neutral hydrogen, might map reionization in detail, revealing when and where it occurred. The formation of galaxies through mergers and accretion continues throughout cosmic history. Small galaxies form first, then merge under gravitational attraction to form larger galaxies. This hierarchical growth, predicted by theory and observed through studies of galaxies at different distances, explains how large modern galaxies assembled over billions of years. Our Milky Way formed through this process. The oldest stars in our galaxy, found in globular clusters orbiting in the galactic halo, formed over 12 billion years ago in smaller galaxies that later merged to form the Milky Way. The galactic disk, where the Sun orbits, formed later as gas settled into a rotating plane and continued forming stars. Evidence for this merger history appears in stellar populations. Stars in the halo move on elongated orbits, inclined at various angles to the galactic disk, reflecting their origin in different smaller galaxies. Some stellar streams, remnants of disrupted smaller galaxies, can be traced orbiting through the Milky Way. Material from ancient mergers still visible billions of years later. Similar merger histories characterize other large galaxies. The Andromeda Galaxy, our nearest large neighbor, shows evidence of past mergers and continues accreting smaller galaxies today. In approximately 4 billion years, Andromeda and the Milky Way will begin their own merger, eventually combining into a single larger galaxy over billions of years. Supermassive black holes, containing millions to billions of solar masses, reside at the centers of most large galaxies. These objects, despite their enormous masses, occupy relatively small regions, with event horizons only millions of kilometers across for the most massive examples. How supermassive black holes grew so large remains partially mysterious. They appear to have existed when the universe was less than 1 billion years old, requiring rapid growth during early cosmic history. Possible formation mechanisms include collapse of massive gas clouds, growth through mergers of smaller black holes, or direct collapse of very massive first-generation stars. Observations of distant quasars, powered by matter falling into supermassive black holes, reveal that these objects existed remarkably early. Some quasars observed, when the universe was less than 1 billion years old, contain black holes exceeding 1 billion solar masses. Understanding how they grew so massive so quickly remains an active area of research. The relationship between supermassive black holes and their host galaxies shows interesting patterns. Black hole mass correlates with properties of the galactic bulge, particularly the velocity dispersion of stars in the bulge. This correlation suggests black holes and galaxies co-evolved, influencing each other's growth through feedback processes. When matter falls into a supermassive black hole, it releases enormous energy, often producing jets of particles moving at nearly light speed and radiation across the electromagnetic spectrum. This energy can heat gas in the surrounding galaxy, potentially regulating star formation by preventing gas from cooling and collapsing. This feedback, connecting black hole growth with star formation, helps explain observed galaxy properties. The large-scale structure of the universe, revealed by surveys mapping millions of galaxies, shows patterns reflecting cosmic history. Galaxies concentrate along vast filaments and sheets separated by enormous voids. This cosmic web structure, spanning hundreds of millions of light years, emerged from tiny density variations present during recombination. Simulations of structure formation, starting from initial conditions matching the cosmic microwave background, produce cosmic web patterns remarkably similar to observations. Dense regions attracted surrounding matter, growing denser and pulling in more material. Less dense regions, losing matter to denser neighbors, became increasingly empty. Over billions of years, this process amplified initial variations into the structure we observe. The cosmic web represents the largest organized structure in the universe, beyond scales of a few 100 million light years. Matter distribution becomes roughly uniform when averaged over sufficiently large volumes. This transition from structured to uniform, predicted by theory and confirmed by observations, supports our understanding of how structure formed. Dark matter plays a crucial role in structure formation. Simulations without dark matter fail to reproduce observed structure. With dark matter, simulations match observations well, suggesting our understanding of gravitational structure formation, at least in broad outline, is correct. The universe we observe today, 13.8 billion years after expansion began, contains structure at every scale. Planets orbit stars, stars cluster in galaxies, galaxies group into clusters, clusters connect along filaments forming the cosmic web. All this structure emerged from tiny quantum fluctuations during inflation, amplified by gravity over billions of years. Understanding this evolution, from nearly uniform early universe to structured modern cosmos, represents a major achievement of cosmology. The theory, combining general relativity with quantum mechanics and particle physics, successfully predicts observed structure when provided with initial conditions measured from the cosmic microwave background. Many details remain uncertain. The exact nature of dark matter, the fundamental physics of dark energy, the precise mechanisms of galaxy formation, the growth of supermassive black holes, the detailed history of reionization. Each represents an active research area with ongoing observations and theoretical work. Future observations will continue refining our understanding. Next-generation telescopes will observe even more distant galaxies, probing earlier cosmic epochs. Gravitational wave detectors might detect primordial signals from inflation. Improved measurements of cosmic expansion will constrain dark energy properties. Searches for dark matter particles continue, attempting to identify this mysterious component, the beginning of the universe, while occurring nearly 14 billion years ago, remains accessible to investigation through the evidence it left. Every observation, from the expansion we measure to the radiation we detect to the structures we map, provides information about cosmic history. From this evidence, scientists reconstruct what happened, testing predictions against observations, refining models as new data arrives. This process of developing theoretical frameworks, making predictions, testing through observation, represents science at its most powerful. We cannot directly observe the early universe, but we can detect signals that originated then and traveled across cosmic time to reach us. We cannot witness structure formation over billions of years, but we can observe many examples at different stages and reconstruct the process, the story that emerges of evolution from hot plasma through recombination, formation of first stars, assembly of galaxies, and development of cosmic structure matches observations across independent tests. The cosmic microwave background properties, element abundances, galaxy distributions, expansion history, each provides independent confirmation of cosmic history reconstructed from theory. Of course, our understanding evolves as observations improve and theory develops. Models refined over decades through countless observations and theoretical advances represent our current best understanding. Not final truth. Future discoveries might require modifications or reveal new phenomena demanding explanation. Yet the broad outline, expansion from a hot, dense beginning, appears firmly established. Too many independent observations, too many successful predictions, too much agreement across different methods all support this framework. Whatever refinements future discoveries bring, they will likely modify details rather than overturn the fundamental picture. The universe began expanding nearly 14 billion years ago from an incredibly hot, dense state. It underwent inflation, a brief period of exponential expansion. It cooled through various transitions, forming particles, then nuclei, then atoms. It became transparent when recombination occurred, allowing light to travel freely. Structure formed as gravity amplified tiny initial variations. First stars ignited, galaxies assembled. The cosmos evolved into the vast, structured universe we observe today. This history, reconstructed from evidence we can observe, reveals the origins of everything we see. Every atom formed during nucleosynthesis or in stars. Every structure emerged from gravitational collapse of matter. Every galaxy assembled through mergers and accretion over cosmic time. All of it traces back to that beginning, that moment when expansion started and set everything in motion. Understanding this history, connecting observations across 13.8 billion years, represents one of humanity's great intellectual achievements. From our vantage point on one planet, we've mapped cosmic history from earliest observable moments to the present, traced the formation of structure across the universe, and identified the processes that shaped everything we observe. The universe continues evolving. Stars continue forming, though at declining rates. Galaxies continue merging. Expansion continues accelerating. The same processes that shaped cosmic history continue operating, following the same physical laws, producing ongoing change across cosmic scales. We observe all this from a particular moment in cosmic time, neither beginning nor end, but somewhere in between. The universe existed long before Earth formed. It will continue long after Earth no longer exists. During this overlap, during this brief window when conditions allow observers to exist, we can study cosmic history, trace our origins, and understand the processes that gave rise to everything. The beginning, that moment nearly 14 billion years ago when expansion started, determined much about what followed. Initial conditions, set during inflation, influenced all subsequent evolution. The balance between matter, radiation, and dark energy shaped expansion history. Quantum fluctuations, stretched to cosmic scales, seeded all structure. From those initial moments, through physical processes we can study and model, emerged the universe we observe. Stars formed and died. Elements heavier than hydrogen and helium accumulated through stellar processing. Galaxies assembled and evolved. Structure developed across cosmic scales. Eventually, on at least one world, conditions allowed life to emerge, life that could eventually study its own cosmic origins. This represents perhaps the most remarkable aspect of cosmic evolution. The universe, through natural processes operating over billions of years, gave rise to structures complex enough to study the universe itself. Matter organized into patterns that could observe measure, think, and understand. We are products of cosmic history. The atoms composing us formed in the early universe or in stars. The planet we inhabit formed from material processed through stellar cycles. We exist because the universe followed a particular evolutionary path, one that allowed planets, chemistry, and eventually life. Understanding the beginning helps us understand this path. It reveals where we came from, in the most fundamental sense. Not just biological evolution on Earth, but cosmic evolution over nearly 14 billion years, from hot plasma to structured universe containing observers. The evidence for this history surrounds us. We detect it in radiation-filling space. We measure it in cosmic expansion. We observe it in element abundances. We map it in galaxy distributions. Every observation adds detail. Every measurement refines parameters. Every discovery extends understanding. The story continues unfolding as observations improve. New telescopes probe deeper into space and farther back in time. New detectors search for signals from earliest moments. New theoretical developments attempt to explain currently mysterious phenomena. The process continues, driven by curiosity about origins, by desire to understand cosmic structure, by recognition that understanding the universe deepens understanding of ourselves. As we conclude this exploration, we return to the present, to this moment, 13.8 billion years after expansion began. The universe surrounds us, filled with structure on every scale, all connected through cosmic history, reaching back to that beginning. Understanding this history, tracing these connections, represents ongoing scientific endeavor, one that continues revealing the origins and evolution of everything we observe. Good night.